Before we begin, we're going to quickly look at what faults are. So what exactly is a fault? A fault is any surface or narrow zone which has a visible shear displacement. There are three types of faults: normal faults, reverse faults, and strike-slip faults. A fault will be considered normal if the hanging wall has been displaced to a lower level than the footwall. If it is vice versa, it is considered a reverse fault. If the movement is lateral along a horizontal plane, the fault is regarded as a slip-strike fault. Why is this important, you may ask? Well, the idea that I'm proposing is that fault thickness affects the amount of faults that can develop along a bed. To do this, I will be filling a box with sand. What a wonderful idea, you may be thinking to yourselves, and it is. This sandbox, like the one presented on the screen, works by filling it with sand and then using a wedge to compress the sand, which will in turn create a fault, or fault in. Whilst compressing the sand, you will need to measure a variety of things, which are presented on the screen. To test this idea, I'm using two sandboxes. The first sandbox will be a thickness of 2mm, and the second sandbox of a thickness of 5mm. As you can see from the graph on the bottom left, thickness does actually play a role in fault development. Sandbox 1 has developed 8 faults, while Sandbox 2 has only developed 4. This isn't accurate reading, since there are other factors which influence faulting. Just to list a few are porosity of the rock, as well as density of the beds. I wasn't able to use the density of the beds correctly, since I ended up using just sand rather than sand and talc, which gives a better reading and a representation of faulting and how bed thickness can affect it. As seen in the other graphs, thickness also affects much more than just the development of faults, as well as the amount of faulting occurring. It also affects the overall wedge size, as you can see in the wedge graph. Sandbox 2 has thicker wedges, whereas Sandbox 1 has thinner wedges, but more consistently it has 2 wedges rather than Sandbox 1. Thickness must also play a major role in the dip of faults. As you can see in Sandbox 1, the dips are much more sharper than Sandbox 2, where they're more shallow. This therefore means bed thickness impacts faulting and the dips of these faults overall. One such place which has faults is the Himalayan orogeny. The Himalayan orogeny is home to a frost fault, which spans across 2,900 kilometers of the Himalayan belt. The central thrust of the Himalayas is a thrust fault, which has a northwest to southeast direction of a strike. The Himalayas is quite thin-bedded. This could explain the reason why there are so many faults there, which would also be backed up by my sandbox experiment, which proved that more faults occur in thinner beds. In conclusion, the thinner the beds are, the more faults there will be, but there was also obviously much more factors towards this which I've explained earlier. This concludes the video overall. Thank you for watching.